Hello, everyone. Welcome to KLAREN follow-up webinar. First of all, thank you for your time and registration. And as you know that this is a follow-up webinar. We had earlier webinar in the month of October. And today we are going to talk about 3 cases. 2 of them are from Asia and 1 of them is from Europe. And you will learn something new today. That's what we hope. And also today's agenda, our objective is to deep dive into technology and explain more about it. Next slide, please, Marco. Marco, next slide. Yeah. So before we begin, some practical suggestion. You can see orange arrow towards red, towards right top of your screen. So in order to enjoy a full screen, just click on it. In addition to that, all of you are on mute, so you cannot talk, but you can type all your questions. We have decided to answer them after a certain interval of each case, so that we'll have more interaction. And please feel free to download 4 handouts. One of them is also today's presentation, so that you can have it handy for your future record. And the last but not least, the recording of webinar will be shared to all the participants in coming days. Next slide. Yeah, so this is the link of earlier recorded webinar where we had introduction about technology and some other useful information. So please feel free to watch it. The video is being already uploaded on YouTube. Thank you, Marco. Next slide. Yeah, about Klaren International and speakers. So myself, Amol, and I'm sales manager of Klaren International. My responsibility is to sales, marketing, and the strategies, and also work on growth plan with the help of management and our parent company. I have Mr. Marco van Beek. He is the one of managing directors and CTO of Klaren International with PhD in fouling. He enjoys solving those critical problems of customers. And you know that we are a part of Evaporator group, which is a German-based family-owned company. They are also early pioneer of cleaning technology, which will focus into tube cleaning with the help of special sponge balls, and they also provide a solution of water filtration system. So we are an engineering and technology company. We sell complete engineering product as per the customer requirement. In order to do that, we cooperate with a network of specialists from all over the world, and our team of process and mechanical engineers sits in India and Netherlands. So to summarize, we design, engineer, and commission those complete technology and the package. And the manufacturing is outsourced locally in order to optimize cost and also to improve lead time. Next slide, please. As you can see that our presence or the local support is throughout the world. So it doesn't matter which part of the globe you are, our personnel will be happy to visit your plant and discuss further in detail. And also, before we make feasibility report for you, there will be personal discussion if required. And we have offices which you can see the black spot offices from our parent company Evaporator, and the client offices, as I already mentioned, we are in India and Netherlands. So we have a worldwide support network. So next slide. Without further delay, I would like to for this this presentation to Marco, and you can see in his background we have our demo unit where we try to optimize processes and based on any inquiries from the customer. If you are visiting to Netherlands, please feel free to visit our office, and we are happy to show you demo unit. So Marco, over to you. We are going to discuss 3 cases here, and I'll come back to you with question and answer session later.
Yeah, thank you, Amol, for the introduction. Like you said, the topic of today is that we will have more deep dive into 3 cases, 2 of them in Asia, 1 in Europe. So the first one is about a new designed and built multi-effect evaporator plant in Asia. The second one is also an evaporator plant, but is unique in the sense that the self-cleaning is combined with mechanical vapor recompression. And the third topic that I will discuss today is a heat exchanger for an edible oil refinery in Europe, where we are providing a solution to overcome their fouling problems. Before going into those three special cases, we find it important to again explain our self-cleaning technology, because we have seen from the people that have registered that many are new, so have not seen the first webinar yet. I mean, at least not to our knowledge. So it's good to repeat this for a moment, so that we all know what our self-cleaning technology is about. Our self-cleaning technology is based on the fluidized bed of cleaning particles at the inside of a vertical shell and tube heat exchanger. And I will start the animation so that you have also a bit of an idea of how it works. What we do is we supply cleaning particles at the inlet of a shell and tube, a vertical shell and tube exchanger. And those cleaning particles are fluidized with the upward flow in the inside of the heat exchanger tubes. And on average, those cleaning particles will move upward. So in fact, the tube velocity is somewhat higher than the falling velocity of this swarm of particles. So they will move upward in the tube. And at the end of the heat exchanger, we will separate them again from the liquid, such that we can recirculate the cleaning particles back to the inlet, to the downcomer, which you see here on the right side. And the cycle can repeat itself, whereas the liquid that is heated, or in other applications it's cooled, will flow to the next step of the process. So the core is fluidization of cleaning particles at the inside of this tube. And if you then would zoom into such a tube, you would see this fluidized bed of cleaning particles, where all the particles in a chaotic manner move inside the tube. And in this chaotic manner, they will impact each other, but they will also impact the tube wall. And it is these very light impacts that in fact give the scoring action of the particles and give the cleaning effect. And this is a light scoring action, meaning that the particles and the impact of the particles is capable to remove the development of a fouling layer, but it's not capable to erode the tube wall. So this fluidization, this impact, is in fact the mechanism behind the cleaning technology. Another aspect of the particles, which I also should mention, is that the particles greatly improve the heat transfer. So they, and that's a bit of a technical term, they will mix the boundary layer, effectively making the boundary layer thinner. And by making it thinner, they improve heat transfer. And the local heat transfer really can improve with a factor of 4 to 5. So that is a great contribution to heat transfer. On the other hand, we must say that we use lower velocities in the tubes than a normal conventional shell and tube. Meaning normally you would apply velocities between 2.5 and 3 meters per second for a normal design shell and tube. But in our case, we are below 1 meter per second. And this makes also that, of course, if you lower your velocity, your local heat transfer will reduce. But with the augmentation of the fluidized bed particles, you will see that we will get to the same level of heat transfer as for the conventional heat exchanger. But with one main advantage is that the heat transfer will remain constant over time. What I also should tell is that we want to control the amount of particles that we feed into this system. And this is what we do using the control flow. So the control flow is a small side stream of the main flow, which we take and which we use to push the particles in. If we stop the control flow, also the transport of particles stops, you can stop the heat exchanger. Second point to emphasize is that where we feed particles to the heat exchanger, what we call the inlet channel, is a really important part, because you can imagine if you want to distribute particles over 563 tubes, then it's a lot more complicated than if you need to do that over 5. So core of our technology is that we know how to design this inlet channel in order to make sure that all tubes have an equal amount of cleaning particles. So by having this fluidized bed cleaning system in place, as long as we remove the layer faster than it can develop, the net effect is that the tube wall remains clean. And this is in fact exactly what we want, because we see that in many cases in industry we have fouling of a heat exchanger, meaning we have the formation of an insulating layer on the heat exchange surface, and this gives rise to all kinds of cost, leads to reduced capacity, cleaning cost, more energy. So a lot of unwanted effects that we can solve with adapting this technology. If we then have a look at where this technology can be applied, well, then that's a wide range of heat exchangers applications. So that goes from heat exchangers that have crystallization, polymerization of particulate fouling, so in the wide range. For example, we have changed spiral heat exchangers from the pulp and paper industry, but also we have worked on reboilers in the chemical industry, heat exchangers in the black or in the pulp and paper industry for white water or black liquor. Another application is thermal desalination of brackish and seawater, so water with a lot of salts, which you also see in effluents of wastewater. Preheat is in the crude oil industry. Unfortunately, we don't have a commercial application there, but we have done tests that really has shown the performance of the fluidized bed. Heat exchange geothermal brines, so brines also containing a lot of salt, silica, giving really at high temperatures big fouling issues we have worked on. Another also important application area is the mining industry. And it's good to maybe say a little bit more words about that, because what I did not mention in the previous slide is that the fluidized bed also has a good impact on viscous slurries like you have in the mining industry. Because by the action of the fluidized bed, by the internal shear that you generate, you can reduce the local viscosities, making it better pumpable, improving heat transfer, and having a better performance. Another area of concern is evaporators for almost all types of wastewaters that contain salts, but also sometimes contain organics. Where the fluidized bed technology has shown that we can concentrate, avoiding and even going to higher concentrations. The last application to mention is Isolary generators. Maybe not Isolary generators in total, but more every time that the heat exchanger would face fouling by the formation of an ice layer, same phenomena as fouling, also an insulating layer, the particles are also able to remove this ice layer from a wall. And we see this currently more and more in systems that want to take heat from surface waters as a renewable energy source for heating households, heating industries, so by the use of heat pumps. But where the limit is that some surface waters in wintertime can approach the freezing condition, and then a normal heat exchanger would stop, where our heat exchanger would still be able to recover heat from this water. So all in all, a wide range of application, but that's not the topic of today, because the topic of today is to focus on some of those cases. And the first one that I will present to you is a new build multi-effect evaporator plant that we have designed, constructed, erected, and now partly commissioned for a client active in making dye stuff. Dye stuff is used to color fabric, to color textile, and from this process they get effluent which needs to be treated before they can dispose it. And in fact, this is an important project for us, because our activities in this sector started with a revamp project for the same customer, where the customer said, okay, please retrofit, change this existing evaporator. So it's not that in all cases we need to build new equipment, we sometimes can also modify existing equipment. So we were also retrofit an existing first effect of an evaporator plant with our self-cleaning technology. We did this by install equipment like the inlet channel, like an outlet channel with the particle separator, a downcomer. We need to, in this case, to shift the vapor liquid separator. But after the retrofit, we really had a very positive impact on the evaporation capacity, because that was also the reason why we were approached by the customer. What we saw before is that the evaporation capacity reduced from, let's say, design capacity around 4.5, 4.8 cube per hour, till half only in an operating period of 300 hours. So that is around 10, 12 days. And this customer was really looking for a solution for that problem. So we installed, as said, the self-cleaning evaporator. We retrofitted their installation. And after the retrofit, you see the performance with the red triangles. And you see that in the period in this graph of 800 hours, that the evaporation capacity fluctuated a bit, but on average was completely and perfectly constant. So this was also really to the comfort of the client, who then asked us to also equip new desired MEE plants with the self-cleaning technology. So this was for us, of course, a very nice step up, showing the performance and also showing the trust in us as an organization, because we find it really important that the customer is not only happy in the first week after that we do the commissioning, but also in the year after. So we have an intimate relation just in order to improve the plant performance. Zooming a bit into this case in terms of design. In the design of this 4-effect plant, we have chosen to use a TVR. A TVR has some pros and cons. The most important is that a thermal compressor, the TVR thermal compressor, it improves the energy efficiency, because you take part of the vapor from the first effect. In this case, can also be the second effect, but in this case we've chosen the first effect, and you use that to mix with the motive steam, as they call it, to generate a mixed steam flow for the first effect. And since you use part of the vapor generated, this is an optimum energy configuration, which in fact you will also see in the Mvr. But I will talk about more about that later. We have also chosen to equip 2 stages of this multi-effect evaporator plant with self-cleaning. And the reason for this is that the assignment we had was to make to design a really optimized plant in terms of heat transfer area, to make a compact plant. And the only, let's say, way you can do that is in fact increasing the temperature difference, and this normally would give fouling issues. But since that we have 2 stages with self-cleaning, we know that this will keep the heat exchanger surfaces clean, so we could do that. So with the same amount of heat transfer area, in fact, we can do a more evaporation rate. The third point to mention is that we have carefully looked at where can we still regain energy from waste heat sources. I will show you that later. So we have made an optimized preheat train. To give you a bit of idea about the specification of the plant, we were talking about a feed intake of 16 cube per hour. But what is really more important is the evaporation rate. So that is around 14,500 kg per hour. So you can see that's almost 90% of the incoming feed. Of course, if you want to have less concentration, so your inlet concentration is higher with the same outlet concentration, you can also take in more feed. But the core is really the evaporation rate that is promised. The steam consumption is around 3.8 kg of evaporation per kg of steam, which is quite normal for this type of plant. And the concentration that we reach is in the final concentration is around 35%, where we already have some solid formation, but not that much, because in this case the effluent is sent to a spray drying plant, which will at the end make for the conversion to ZLD. Looking at the composition of this effluent, we're talking about an effluent with gypsum as the main salt, also giving the fouling issue, in combination with a very high COD. And this COD with temperature will also give coking as one of the contributing fouling mechanisms. Looking at project status, at this moment we can say that 3 plants have been commissioned. The other 4 plants were still in the mechanical erection phase. We hope to start commissioning of the last 4 by early next year. But 3 plants have already been commissioned and taken into commercial operation. This moment performance looks good, but of course we are monitoring that to see if there's any improvement to make. Because still, we only have 2 stages with self-cleaning, meaning that the 3rd and 4th effect still can give fouling problems, but there are also ways to at least minimize the effect of that. 2 stages with self-cleaning. I already spoke about the higher temperatures that we apply. So we see in many evaporator plants that the temperatures in the first effect are limited to 90, 98 degrees. Here we go even up to temperature in the vapor liquid separator of 127 degrees, meaning that the shell side temperature of the first stage is around 140. So a substantial temperature, but which also gives the total larger driving force, keeping heat transfer area small. So you see at the top the cascade of the different temperatures, where the bottom temperature 60 degrees is set by, in fact, the condenser design. As said, in the plant we have looked at the various ways to optimize energy and efficiency. Preheated train, the first preheater makes use of the vapor that normally would go to the condenser. So we take part of this vapor, around 1/5, to preheat the feed that comes in as 30 degrees. So 60 can still transfer the heat to 30. Heating up the feed before it goes to the second preheater. And the second preheater is driven by the condensate of the last effect. After the second preheater, we go to the last preheater that is driven by the condensate that comes from the first effect. So we use the full condensate stream to run through this the preheater, and giving the final push to the feed temperature before it enters the first effect. In this case, we talk about a forward feed plant. One other thing we have done to improve the steam economy is to use condensate flashing from the second till the third effect, and from the third effect to the fourth effect. So based on the pressure difference, you have some flashing then of this condensate stream in the shell side, releasing heat and improving the energy efficiency. Then we come to the part where we would already ask you to, if there are any questions about this case.
Yes, Marco, thank you for interactive explanation of this case. I hope our audience have learned something new today. I received 3 questions, but one of them you already answered during your presentation. Maybe we can go through 2 questions, and then let's say we have 30 more minutes after, let's 35 minutes to go through other 2 cases and remaining part. The first question which I see here is, can you please explain again why it was chosen to have 2 stages with self-cleaning?
Yes, I can. The reason was that the client wanted, in terms of investment, an attractive plant, and the investment is also influenced by having 2 stages of self-cleaning, but it's also influenced by heat transfer area, because every square meter of heat transfer area has a certain investment cost, because it concerns metal, and with the current increase in metal prices, of course, it's really relevant to look at that. But if you want to reduce heat transfer area, you need to increase the driving force of a heat exchanger, of any heat exchanger. That means increasing the temperature difference. You can do that because the fresh steam has enough pressure, but in a normal evaporator plant, you would then enter into even more serious fouling problems because of the higher temperatures. Since we have the fluidized bed active, we do not need to worry about that too much, because we will keep it clean. And this is why we could increase the steam temperatures. And by doing that, in fact, we needed less square meters of heat transfer area.
Interesting. Thank you. Let's switch to second question. Can you please explain the preheater arrangement in the plant design? Maybe you can show that diagram again.
Yeah, so what we see in many plants is that in fact, the vapor from all the effects is used in the next effect for both a preheater bundle and for the heat exchanger bundle of the calendar of the evaporator. meaning that you really use your primary source for preheating. Here we really have looked at using waste streams. So waste streams, waste energy streams that normally would leave the plant. So we've taken part of the condenser vapor as the first step. We are using the final condensate, which otherwise also would be at a too high temperature. And we have used the condensate of the first effect. You could still debate that you could also use the condensate flashing from first to second, but in this case we have chosen to have 3 plate heat exchangers in series. Preheating the feed from around 30 degrees to close to system temperature.
Okay, thank you. I think we can have only these 2 questions, and if time permits, we can go with another questions towards the end of the webinar. So we can now talk about case number 2. Over to you again, Marco.
Yeah, so case number 2 is also evaporator plant, but with one unique, with some unique features. But one of them is that self-cleaning is combined with a mechanical vapor recompression. I will say more about the concept of that in the next slide, but it all has to do that you, instead of using steam or vapor as a driving force, you use, you still use the steam, but you use the steam from the same evaporator by upgrading its quality by using a compressor driven by electrical energy. In this case, we talk about a ZLD plant, meaning that the plant aims to provide only solid waste and make a maximum recovery of the water content, which is, in terms of water scarcity, of course, very beneficial. The client already had installed an RO plant, so that's a very good thing, because in terms of energy efficiency, it's good to use membranes as a first step of concentration. But membranes have their limit, and thereafter, so I think 80% of the volume is already recovered. And the last 20%, if you want to come to ZLD, evaporation is a good choice. So in this case, they have asked us to together with our partner in Asia, to come with an evaporation plant, followed by a centrifuge. So in the evaporation plant, we push the concentrations, meaning that we push it until the moment that we have crystal formation in the evaporator, and effectively the evaporator has become a crystallizer. So the centrifuge we use to take out the solids, and then the remaining molecule is resent to the evaporator. In this case, if you would not have a, would mean that you have a buildup of impurities that don't crystallize, that will only give problems with an even higher boiling point elevation. So you do need a small purge. And in this system, in this plant, the purge is sent to an ATFD, where the ATFD dries it until powder form. So in fact, we have 2 outputs of solids. That's in the centrifuge, directly the crystals, and then the ATFD, the remaining impurities. With an MVR, we talk about a single stage, but I will say something about that later as well. It's equipped with self-cleaning, as said, and uses an MVR. MVR needs a compressor, and in this case, since the feed flow and evaporation rate is on the low side, I mean, low side is always relative, but low side, if you talk about centrifugal compressors, we have chosen to use a roots blower. For the roots blower, we have chosen to use a compressor with a ratio of 1.7, balancing heat transfer area with power cost, but also there more detail to follow. But in overview, the blower in this case will consume around 45 kilowatts. The concentration that we want to achieve is at least 45%, but I have to say that you never know exactly the specifications of the effluents in terms of composition. That we do want to test, how far we can push the concentration, and at both moment we will have the solid formation and also the right quality of solids in the centrifuge. So this final concentration will also depend on the commissioning, which will start in a week's time, and we expect to have the first results by the end of this year. One thing which I forgot to say is that we talk about an RO reject that contains both sodium chloride and sodium bicarbonate as the main species that will crystallize and also will give issues with possible fouling formation. Besides this, that also can give complex salt components. So saying something more about MVR and why we find MVR attractive. There are two reasons. In short, that's the energy efficiency. And the second one is that with an MVR, based on its principle, there is only one effect. And with a multi-pack effect evaporator plant, there are more effects because you need that to improve your energy efficiency. But then the question always is, when we talk about a multi-effect evaporator plant, how many effects that should be equipped with self-cleaning. And as you have seen in the previous case, we have chosen to equip 2 stages with self-cleaning. That is not always possible, also not based on the economics if the temperatures are too low. So then you only would tend to have one effect equipped with self-cleaning, but then the question is which one? The highest temperature, so the first stage, combined with, or let's say there's an alternative, the last stage where the temperatures are lower, but the concentrations could be higher. This will depend on also the experiences that a customer has had before, but this discussion is always there. And when you talk about an MVR, yeah, this question becomes obsolete because there is only one effect. Because how does this MVR work? Well, it works on the basis that if you look at the energy consumption of evaporation, it has to do with the heat that you put in to convert a liquid to a vapor, so in the latent heat. And this is really taking a lot of energy to evaporate 1 kg of water. So you would like to recover this as much as possible. And that's why in a multi-effect, you use it in more stages. Still, some vapor will go to the condenser. In an MVR, all the vapor generated will be condensed in the same heat exchanger. But this heat exchanger can only work if this vapor is then of a higher temperature, because otherwise you have no driving to transfer the heat from the shell to the tube side. So how do you get to a higher temperature? Well, you can do that by increasing the pressure, because if you increase the pressure, then the temperature at which it will condense at that pressure will increase. So that's the main principle. You use a compressor to increase the pressure, thereby increasing the temperature, and thereby you can use the vapor as your heating medium on the shell side of the heat exchanger. And at this shell side of the heat exchanger, which you see here on the left, you will condense all the vapor, meaning that you will recover all this latent heat that you have first put in. And the only energy really that you require is this energy of the blower. This energy of the blower, required energy of the blower, will depend on the compressor ratio that you choose. But more about that in the next slides. But it's also important for an MVR evaporator that you do need to preheat your feed, because the feed enters too cold the unit, you lose too much heat, and that could bring you to failure of the system. So there's always a preheater required to preheat the feed so that it becomes very close to the system temperature. So MVR, positive for energy efficiency, and because there is no discussion anymore which effect of the multi-effect evaporator plant to equip with self-cleaning. Lastly, also to tell you something, a compressor, which I already mentioned, there are 2 types that one can choose. For the smaller flows, one would tend to go to a roots blower. So in fact, a quite simple machine, of course still delicate, but relatively a simple machine, effective, although making a lot of noise. The other alternative is, which you tend to use capacity flows, is a centrifugal compressor. Also has a bit of higher efficiency, but it can only work from the higher flows. To zoom in a bit on how big this effect is on the energy consumption of an MVR compared to an ME. This is also worked out in a white paper, which is enclosed with this webinar as a handout, so you can read more about it there. But the core is that as I already explained, that you use all the latent heat to recover that in the condenser section of the heat exchanger. So if you then would really do the mathematics, you need to take some assumption to convert the, for example, in this case we have taken coal as the primary source. If you want to convert coal to electricity and to steam, you need to take some assumptions about efficiency, which you can see on the right. And we need to take a starting point for the compressor that we use for the M. So in this case, we have taken a two-stage compressor having a delta T of 17 degrees. And then you can calculate that the energy that you use, the electrical energy for the MVR, is around 0.06 kilowatt hour per kg of evaporation. Where for a multi-effect evaporator plant, you have both steam consumption, but you also have the electricity consumption for all your circulation pumps, for product pump. No, that would be the same for the MVR, but the circulation pumps, of course, are very important for an MEE plant, but also for the condenser, for the cooling tower. So there you would see that we would need 0.28 kg steam per kg evaporated and around 0.03 kilowatt hour for the same amount. So you see that the electrical energy is already half of the MVR plant, so it's a substantial part. If we then convert those both energy uses to the amount of coal that you would need to evaporate 1 cubic meter of water, you would get to 43 kilo of coal for the MVR plant, and almost double for the MEE. So you can directly save 40% of your prime energy input, and that's of course very, let's say, wanted. Although we do realize that in some places of the world and some applications and plants, yeah, the availability of steam is there, which makes it attractive to use that sometimes even waste stream of steam, and not to choose for the MVR. Zooming into three very important and critical design aspects. The first one is, I already showed you some pictures of the compressors. So an MVR involves rotating equipment, where the roots blower might be a bit more simple, having rolling bearings. Lubrication is there, but is less important. Especially the centrifugal compressor is rotating equipment and really requires careful care. Meaning that you need to monitor its performance. You need to be careful that vibrations are in order, that you do not get deposition of dirt on the blades of the compressor. So you really need to take care also to improve the lifetime of the compressor. And in case of a damage, you really talk directly about a lot of money. So something not to forget. MVR with rotating equipment, requires care. The second part, which you see here also in more detail on the right side, is that in the design of an MVR, you're always balancing between heat transfer area and the compressor ratio. Heat transfer area means investment up front in material, in square meters of heat transfer area, and compressor rate is in fact not your investment, but it's your operational cost, because it will determine how much energy that the compressor requires. To give you an example, if the compression ratio is 1.4, then this blower for this typical case would require 26 kilowatt. But if you increase the compression ratio to 1.7, it becomes 42 kilowatt. So if you put 42 as 100%, then the compressor ratio of 1.4 is almost 40% lower. So really important. But this has an other side of the coin. And the other side of the coin is that if you choose a compressor ratio of 1.4, then the temperature increase over your blower is only, compressor, it's only 7.7 degrees. And if you go to 1.7, this temperature increases to 13. Temperature difference is directly the driving force of the heat exchanger, so it's directly related to the heat exchanger area that you need. But this has one aspect that I also should refer to, and that's boiling point elevation. Boiling point elevation you will have with effluents, since the composition of the effluent with salts and with its concentration will make that the boiling point increases, meaning that if I have a water with a salt, it will at the atmospheric conditions not boil at 100 degrees, but maybe at 103 degrees. But still, if I evaporate at 100 degrees, it will still condense, because then it's water again at 100 degrees. So this boiling point elevation I lose when I look at my heat exchanger design. In other words, suppose I have an increase of temperature over my blower of 7.7 degrees, and I have a boiling point elevation of 3. I only have 4.7 degrees left, which of course will have its effect on time. And that's also what you can see in the most top table. Looking at the top side, for example, case A and B, both with a compression ratio of 1.7. If the boiling point elevation increases from 3 to 6, my heat exchanger area goes from 100% to 142%. So a substantial impact. If I then look at the difference in compression ratio, for example, with the same boiling point elevation, so comparing A and C, you see that for the same boiling point elevation, when I reduce my compressor ratio, because I want to use less energy during the runtime, my heat exchanger does not need to be 100%, but I need to go to 217%. So you see, I can go to a lower energy consumption over time, but then I need to increase my heat transfer area. Case on case, with customers, we can see what is the most optimal for their case, but it's really important to realize that you're always balancing between investment and operational cost. The third element that I would like to describe is that it's important for an MVR that there is a positive energy balance, and that there's really this importance of the preheater. To illustrate that, we can have a look at the balance between energy input and energy use. So the energy input comes from the vapor that is condensing on the shell side. So there is a certain amount. Here the bottom block, energy in water vapor of the shell side. The second energy input that we have is that a compressor will always have some water injection. This is to control the outlet temperature of the vapor, because otherwise it will be superheated, and you don't want that based on temperature profile in your heat exchanger, but also because effectively depends at the pressure defined by the pressure. And also the design of the blower will make that the vendor will say that there's a limit of the temperature that it can be. So there will be water injection, but this water injection later we can condense as well, so that will give us an additional heat input. The second source of heat input can come from the feed when we have upgraded it higher than the system temperature. And of course, if we use the condensate, which by definition has a higher temperature as a system, we could approach that. Still, in many cases, I think it will be almost equal, or maybe even the feed will a bit lower. But in this example, there's energy input from the feed. If we then combine it in where is this heat used, then some heat is lost due to heat loss, due to not proper insulation, and of course the energy is used to evaporate water. So as long as my left side is larger than my right side, in fact my energy balance is positive, so I tend to start to generate a little bit more vapor. But this energy balance can also be negative. So if the energy input from the feed changes to a negative value, then the feed has a lower temperature than the system, or the heat loss is too high, then the right column can become larger as the left column. And that means that I lose more heat than I have as heat input. And this is an impossible situation. So you get a system which is continuously going in a cycle down. And at the end, the system will not work or perform. So really important to consider. So to summarize, MVR important. Think about rotating equipment. That there's always a balance between heat transfer area, investment, and operational cost in terms of energy use. and that it's really important to have a positive energy balance in the thermal design of the evaporator. With this, I come to the final part of this second case.
Yes, thank you, Marco. Very interesting questions related to MER. I think let's go with the question for roots blower. The question from audience is when to choose for a roots blower.
Yeah, a root blower one would typically choose for lower vapor flows, because it has a little bit lower efficiency than a centrifugal compressor, but it is also less costly. So root blower is cheap, is more robust, but yeah, comes with a bit of lower efficiency. But typically for lower vapor flows, it does not make sense to go to the centrifugal compressors. So there, yeah, one would typically choose for the root blower.
Okay, thank you. Maybe second question quickly. The question is, my MVR plant is not reaching its design capacity. There are no further details, but a certain design capacity, and what can be the reason?
Yeah, let's say the offer would always be to think along with the customer to analyze the data and to see if we really can find the root cause. But there are two areas which I would already consider as the areas to look for, and that is one, how has boiling point elevation been considered in the design? Because if this is not properly taken into account, it could be that the plant is completely under designed, and then you cannot reach your capacity, and you see that the blower tends to use more energy than what is offered, because you have to, if you want to evaporate a certain amount and you want to push that, effectively the blower will seek a new operating point which has a higher pressure ratio. So you will see that your plant typically uses more energy than expected. The second area we're looking at is in fact the preheat train. There's not a train, it's only a single plate heat exchanger. But yeah, if this plate heat exchanger preheater is able to get to the right system temperature, because otherwise, yeah, you have a system which simply cannot function.
All right, thank you. I think, Marco, we have 12 minutes to complete our webinar. This is third case. If you could finish the last one in, let's say, 7 to 8 minutes, we can get some time for additional questions and then some announcements. So there's 12 minutes to be there. Thank you.
We proceed with the third case. The third case is a heater and heat exchanger for a plant, a refinery, refining edible oil. So edible oil, before it can be shipped to consumers, needs to have certain treatments. Some components need to be taken out, needs to be deodorized, it needs to be filtered. And in this plant, which they call the refinery, there is an issue with the heat exchangers that heat the oil before it goes to one of the process steps. You see them in the yellow circle. So in the first heat exchanger, we recover heat from another oil source, which is a hot source, having a temperature of around 130, 140 degrees. And we recover the heat from that, and in parallel then heating the primary energy, or the primary oil that goes to process step B. This heater is followed by a second heater which is driven by steam, and what they see in the actual application is that over time they need more and more steam to compensate for the fouling which they have in the first heat exchanger, where in the same time also the second heat exchanger is fouling. So at the end, they cannot reach the desired temperatures, and they don't recover as much heat as possible, meaning that there's really a business driver to look for an alternative. So they have asked us to look at an alternative with the self-cleaning heat exchanger. And you see the location of this heat exchanger in the green. So it will be in parallel over the existing ones. creating also some redundancy. So that was the case. Zooming a bit into the fouling, so the fouling problem as such comes from the impurities in the oil in combination with the filter aid. And this filter aid, which is used in this refinery, is in fact a perlite material which comes from volcanic action. You get a very porous and glassy type of rock. And since it's very porous, they use this to absorb different media or different impurities, and also to use it as a filtering aid, because this perlite will deposit on a supporting mesh, so a stainless steel supporting mesh, will increase in volume by its nature, and will really have a very fine filtering of the media going through. But in some cases, when the pressure would be too high, you can have an overshoot of, in fact, filter aid passing through the supporting mesh, entering into the main system, and together with the other impurities giving rise to the fouling issue. So that's the problem that we wanted to solve. Since it was a new application for us, we decided first to go for a test unit. Doing a test is something which we do more often. If for us the application is new, but also on the other hand, the client wants a guarantee on the performance. So then we together decide to run a test, and we have done that in this plant as well. So always to prove we do the test to prove the performance, to optimize our parameters of fluidized bed. And to have a detailed measurement also of how in the client fluid liquid in combination with the fluidized bed, what the heat transfer coefficients are that we can realize. So we have done this test. The outcome in terms of heat transfer coefficient you see at the bottom. You also see the strong influence that if we have a higher volume fraction of particles, move to the left of the curve. You see that the heat transfer coefficient goes up as per theory, but we really reached very nice heat transfer coefficient this test. Plus that we always monitor the heat exchanger in this test unit over a longer period, and we can show the long-term performance. And we could show, and we have shown, that the heat transfer coefficient remained constant over time. So have shown the long-term performance. Based on this, the client decided to award us with the order for a commercial unit. And at this moment, we are at the start of commissioning of this unit. I must say it's really a unique unit. Of course, maybe people always say that they're from their own products, but in this case, I can tell you why we say it's unique. Because we have a design with a double shell arrangement. So in fact, we have one uninterrupted tube passage of the oil, so that it will go from bottom completely to the top, but we have heat input from two different sources. At the bottom, we have heat input from the oil coming from another process step. And so the hot oil that I was already talking about, we will cool it down and use it to heat up the incoming oil. So this is an oil section with a lot of emphasis on improving the shell side heat transfer by proper design. In total, this bottom bundle is 12 meters in height. And this bottom bundle is then followed by a top bundle, 2 meters in height, which is driven by steam. Why did we have this top bundle in addition? Well, if the temperature would not be matched, for example, because there is also on the shell side a bypass to gain heat for something else, we still have the steam available to push the temperature and improve it till the required set temperature. The other meaning, even more relevant, is that when the plant needs to start up, the refinery needs to start up, there is not a hot oil stream yet available. So we need steam as a startup energy input. So initially, the oil will only be heated by the steam until it's at the required system temperature, and then the other steps of the process will start. And then also the hot energy, hot oil source becomes available to drive the heat recovery part. So this is the double shell arrangement with the tube passage uninterrupted It's not a very big bundle, so we only talk about 61 tubes. For the large evaporator, we go up to 1,000 tubes, so 61 isn't still a reasonable amount. So only 61 tubes with a diameter of 1 inch. But the total length has become 16.5 meters, so that's rather unique. It does give a stable system operation. In this application, we've chosen to use cleaning particles of stainless steel 304 with the 2 millimeter inside. And what is also important to tell that for the particle separator, which normally has an outlet at the top, we have made a special design with a side outlet, which was also completely evaluated and analyzed by the means of CFD calculations. So we are really looking forward to take this unit into operation. With this last slide, I've also come to the last question and answer moment, but I'm
Thank you, Marco. And it's worth to mention that this is world first self-cleaning technology in an edible oil plant, and we're very excited to working forward on this particular plant. We have last 3 minutes. Just now I received one question, which is also let's say good to address. Not specifically for the edible oil plant, but in general. I can read it for you. About the self-cleaning system, when recirculating the particle for self-cleaning, how do you manage to not recirculate the solids and fibers that come with the effluent flow of water?
That's a good question. Some part will be recirculated in the system, but the majority of the part will leave via the particle separator, because normally it is rather small solids, so they will not fall down in the separator but move upward with the outgoing liquid. So in fact, we will leave the system again. So then I could imagine that the second question would be, okay, but so I have an increased flow of those solids. Well, to some extent that's true. On the other hand, what you do have to realize is that in all cases, when you have a heat exchanger that has problems with fouling, those solids will always be in your liquid. Because normal fluid flow only by its shear will already remove part of the dirt of the fouling layer. So this material you will already have in your outlet. But it is of course true that if you remove more with the self-cleaning principle, that the amount of solids can go higher a bit. You would have to, let's say, look at the total amount per unit of time, and then in most cases it's rather limited.
All right, thank you, Marco. I think we can take last question, which was just received related to edible oil plant, because you mentioned 16.5 meter height, and the question is the height of the heat exchanger not giving any issues for your system?
No, in fact, you would imagine this, but we have learned from experience that the longer the heat exchanger, the more stable the system is. So we see that disturbances that you can have, for example, in your volume fraction in the tubes, they will more easily stabilize with the longer heat exchanger tubes. So in fact, it has a positive effect on the stability of the system. Therefore it's even more likely to run better than heat exchanger which has too short tubes. So typically the minimum length of tube that we would need is around 4 meters.
All right, thank you. I think we can move to next part quickly. We are almost finishing our time. Can you go to next? Yeah, so we made an announcement in our last webinar that we will be exhibiting and presenting into Heat Exchanger World Conference in this month, but unfortunately due to new rules in Netherlands with respect to Corona, it has been rescheduled to next year. So unfortunately we are not able to exhibit and meet some of you, which was earlier planned there, but feel free to visit our office, and then it would be great to meet and then and answer to any of your questions I'll also show our demo unit and discuss further in detail. So I think we can ready to have last poll, because we are a sustainable company, and we thought, yeah, why not we check our audience that what are their ways to live more sustainable lifestyle. So you can see poll, and it will take like a couple of seconds to answer and understand how to live a more sustainable lifestyle. So I give like 5 to 7 seconds, and then we can see um, which percentage go to which option. If you are on phone, maybe you can see with small screen. If you are connected to additional screen, that might pop up on second screen. So just answer, and then yeah, I think we are ready to show the result. Yes, so yeah, this is Thai. Better, yes, we should use more renewable energy, and also focus on recycle and reuse. But yeah, nobody wants to use public transport. uh, that is interesting. And with this, I would like to conclude our webinar. Thank you again for your time. And if you have more questions, please contact us on info@klarenbb.com, and we would be happy to answer any of your questions. And yeah, stay safe, stay healthy, and thank you again.
Yes, thank you.
Thank you.